So now I'm going to start on the materials I'm going to mention. I think, again, this is a finance guy talking, not a scientist. And so I see the dollar signs or the euros or whatever. I guess dollars now because it's a strong currency. And so what I'm giving you is a good starting, I think, first lecture to the science work you're going to be doing to give you a sense of where the money is. These are the 5 materials that we see for the next 5 years that are going to have the greatest development potential, the greatest opportunity commercially. And if the work you're doing scientifically, you see a development in your own careers and where you want to be in the kind of places you're going to have opportunities, I think these 5 are certainly great places to consider. We kind of sit at a funny position because of the amount of customers that we work with. We kind of see everything. We sign NDAs with companies, so we don't disclose anything that's ever proprietary. We couldn't be who we are if we couldn't be trusted to put up the walls between various companies and not disclose what everybody's working on. I mentioned what we did with solid oxide fuel cells with GE and Siemens and these others. This was back in 2001. And each one of them had their own technology that they didn't want the other to know about, and yet we were supplying all the materials. So we can be trusted not to disclose proprietary technology. But on the flip side, and this is kind of important for you people, is we have kind of a bit of a slogan in the company, which is we will prevent you from reinventing the wheel or pursuing known dead ends. So if technology is non-proprietary, it's open to the world, you still may not know that what you're working on has already been invented, or what you're working on has already been determined not to work. So a lot of people come to American Elements and say, can you provide us with information on our project? Because we're thinking of spending a lot of money to see this or that. Has anybody else on a non-proprietary basis worked on that project? We've gone through the literature. We don't see anything. Have you guys seen anything? And that's a very common question that comes into the company. And we're happy as long as there's no proprietary aspects to the technology, we'll share what we know to allow your program to develop in the most efficient manner. So the first one here is MMOs. It's a phrase we use. A lot of people aren't familiar with it. Mixed metal oxides. They are almost entirely really dealing with energy generation. They're all lithium based, but there's a lot of work being done now to find that perfect lithium formulation as a cathode material. To give you a little bit of history of where we're at. So for those, I'm sure there's people here that are going to listen to much of my discussion and say, this guy knows this much about what I know because that's my area and I got my PhD in it. I'm about to give a speech on current stuff, and I understand that. So please understand that, again, I'm a finance guy. So the depth of my knowledge is not as good as the breadth of my knowledge. I know a lot of areas, only so much. So the 2 developing materials that I saw from a commercial basis were the ones that are mentioned up here, which is NMC and LFP. And that's where we first started with batteries in the beginning of our company and pretty much commercially for the world, which was the use for solar, both commercially and residentially. And they were both used pretty commonly, but over time, it became pretty clear that they were very different materials with different capabilities. NMC has much higher energy density, and it works far better in cold weather. So that made it an excellent material for certain purposes. But when you use LFP, you've got a much longer stable material, and it's more stable and lasts longer. So what we're seeing right now commercially is that LFP is becoming kind of the battery, cathode of choice in batteries for commercial and residential solar use, and that's kind of the kind of customers we're seeing develop it. Whereas NMC is becoming kind of the automotive because it's got such higher density. You can use a much smaller battery and produce the same amount of energy. So we're seeing kind of a differentiation with NMC going into the automotive. It's part of the work that Tesla's doing, whereas LFP is going to probably be the battery of choice for solar gathering materials. Then there's two more that I should have put up here. They're newer. They're also very, very important. You may want to note them if you're interested in this area. One is LTO, which is lithium titanium oxide. And it is the longest lasting cathode material for batteries. So the primary applications that we're seeing is maritime use. Batteries now on commercial bulk cargo ships, which is now beginning, everything's going to go electric eventually because of global warming. And so we think LTO will be the battery on the big ships. And then the last one is NCA, which is brand new, pretty brand new, which is lithium, nickel, cobalt, aluminum. And that one is one under study. I can't comment much about it, but I know we're working with it. And so those are the big MMO materials. Again, just with what's going on with battery technology, you're all probably much more familiar with it than I am. These are very, very important materials. So that's the first of 5. This, I would say, is probably the most important of the group I'm going to be describing, which is mixines. How many people are familiar with mixines? If you give me a show of hands. Okay, only about 3 or 4 people raised their hands. This is the future of advanced materials in so many different ways. They are magical. I think, in fact, one of the keynote speakers is doing, one of the speakers is doing 2-dimensional materials. Am I correct? Extremely important materials. We're always trying to find the synergies between the big kind of categories of materials: chemistry, metals, ceramics, nanoparticles. They all have features. Mixines combines them all. It has the electroconductivity of metals. It has the forming and thermal protections of a ceramic, and it has the high surface area aspects, because it's 2-dimensional materials, of nanoparticles. Whoops, somebody moved me forward. Not you, huh? The magical cursor elf floating around the room. So we're seeing, I'm just mentioning a couple of applications here, but our first use in the company of mixines was in hydrogen generation. That was back quite some years ago, a decade ago, working with NASA on their efforts to create hydrogen generation facilities on the moon, using the water on the polar caps to create hydrogen to hopefully launch to another location from the moon. And that work is still ongoing. But that use, and that's the need for hydrogen generation in such a small capacity area. Again, you want a nanoscale material, and this is working with 2-dimensional materials. The other recent work we did with mixines, which I think is unbelievably incredible work. We're doing this with a number of companies, which is in the medical application for cancer treatment. And what we're doing is, with mixines, is creating an electrically conductive cation with an anion that is an organic. And what that allows the researchers to do is, you can create an organic ligand that will attach to cancer cells. It'll have an affinity with the cancer cells, which could be metastasized through the body someday. And you ingest this material, the organic ligand then goes out and searches for where that cancer is in the organs, the lungs, if it's metastasized, wherever it might be. And then you radiate the body, and the cation, which is like a copper, will then destroy the cancer cell. Very futuristic work, but it seems to work in research. And so that, again, is an aspect of mixines. Other aspects would be the antennas in cell phones now, because think of how much room you have in a cell phone. These can be used for antennas, so you can put on a two-dimensional layer into a cell phone and use that as the antenna device. Another incredible use of them, this is kind of research for the last couple of years, is developing membranes of mixines, which will be used eventually for desalinization plants and water purification treatment, because you can literally pull molecules out. It's not like screening for particles anymore. You can pull salt out of water using membranes of mixines. You can pull acids, all kinds of materials that you could never previously remove from water can now be removed using mixines. So to me, they are the most incredible of new materials. I think that for everyone other than the 4 people that raised their hands and said they know mixines, I strongly suggest you learn about those materials, because they seem to have applications in just about everything. Number 3, I know you're all excited to see what the third one is. Ceramic fibers. There we go. Thank you. The next 2, this is the first of those 2, still I view as having a lot to do with energy. I mean, that's what I'm saying. Previously, it might have been optical coatings 5 years ago. Everything's about energy right now. And so even the materials, the next 2 I'm going to mention, this is the first one, are structural. They're really about doing those things you need to do for energy to be successful. So ceramic fibers, very exciting new topic. These are often ceramic like chopped fibers. We supply them in a number of different forms. They can be, it's molecule level, micro level, I should say, not nanoscale, embedded in a CMC, which is a ceramic matrix, to form parts. They have the advantage over lightweight metals in that they have much higher thermal tolerance. They're obviously not being a metal and they're a ceramic, they're corrosion resistant. So we're seeing parts all over the automotive, aerospace, rockets being replaced with ceramic fiber created materials. Silicon carbide. The most common you see, and whoops, there we go again. That's not you, huh? I'm sorry, I don't mean to blame this fellow, but I'm not, huh. Okay. So keep that in mind. You may have a little issue here with the clicker. Aluminum oxide fiber embedded in aluminum oxide CMC composite matrix is kind of the one that everybody's focused on, although there are several other materials. I'm not touching it, just so you know.
It's another conference.
Oh, so maybe
they interfere.
Like garage door openers that open each people's garage doors. Okay, no problem. Also silicon carbide, I did mention here, graphite materials. Okay, we'll bounce around. You know what? I'll go to the next one. I'll take us to this one. The other similar example of, keep this in my hand just in case. I titled it aerospace composites, but really it should be PMCs, polymer matrix composites, very similar to CMCs, but they have one incredible advantage. Because it's a polymer, you can actually form parts. So you have still the thermal resistance, the no issue with the corrosivity of a metal, extremely lightweight, but you can also form them. Oh, now I'm back to fibers. You can also form them into shapes and forms. So again, very, very exciting in aerospace. You just ignore my slides, please. I've given up. I've given up. It's no worries. There's so little on there. I think you get a sense. If we go over to the last one, we're fine, which is that one.
Just tell me when you want to change the.
Oh, okay. All right. Well, I'm not touching. Okay, so we'll stay at this one, and then I'll signal to you. I'm obviously running out of time anyway. Silicon carbide, silicon nitride, aluminum oxide, all these can be formed into polymers. Again, aerospace, automotive, rocket, as I say, military, but rockets, also tanks. We're going to see a major shift that's really actually began a couple of years ago, away from using metals for really anything and moving towards ceramic materials with embedded metal matrices or other either carbon fibers, or again, just taking nanoscale ceramic materials, embedding them in polymers, and you still get the strength. You still get all the aspects that you traditionally got from metal that you can get from ceramic. I mean, you've got ceramic tanks now, which have all the safety composites. You have body armor now is all ceramics. It has been metal for a long time. Lightweight, no corrosivity. So this is pretty much the future of all construction materials, structural materials. And then the last one, which, okay, taking the last screen. Surprisingly included is solid oxide fuel cells. As I mentioned at the beginning of my talk, we were involved in 2001 with solid oxide fuel cells. The world was extremely excited. They were going to revolutionize the world, and they just didn't work. They have a problem, a number of key problems, which generally is tied to the electrolyte, which is the biggest one is what we call thermal cycling. If you wanted to use a solid oxide fuel cell for in automotive applications, you're turning a car on and off, on and off, on and off, you will destroy that solid oxide fuel cell. They work beautifully as freestanding power plants that are just allowed to run. But in the kind of applications you'd want to be able to use a fuel cell in, they've always struggled. And we've worked on a number of electrolytes. The biggest ones are the cerium-doped electrolytes, scandium-doped ceria, several others. Those provided protection, but they didn't provide the energy as a YSZ electrolyte, which is the standard electrolyte in solid oxide fuel cell. Typical solid oxide fuel cells are the cathode is lanthanum strontium manganite. The electrolyte is, again, YSZ. And then the anode is nickel oxide, which we've developed, which we're kind of one of the largest suppliers, maybe the largest supplier of that material. A little bit of YSZ for structural purposes in the nickel oxide, but that combination is typically the anode. But strangely enough, they've come back, and there's a lot of work being done on them. Like I said, I'm heading up to Fiat Chrysler after this talk to meet with them. We have a team coming in today. They're going to be there for about a week and a half. I luckily just get to go to the dinner tomorrow night, which is really going to be fun. And they're working very seriously about solid oxide fuel cells for automotive application. There's a lot of work. Mercedes is doing a lot of work on it right now. So surprisingly to me, because 2001 is when I first got involved with them, I think solid oxide fuel cells are very exciting and have a big future. And that's the end of my talk. I hope you enjoyed it. It was a very pleasure. I'm very excited about the conference that's been set up here. It's going to be incredible because the talks look amazing. Thank you all very much for your time. I really appreciate it. Please.
Thank you, Mr. Stewart.
Yes.
We have time for 2 questions or remarks, if someone wants to. Please. Please. You need
Yes, sir.
I'm wondering whether in your company or other that you may know, there is an effort on new materials for recycling to enter the circular economy, which is now very important.
Yeah, my head kind of explodes when you ask that question because there's so many things going on that could be deemed within the universe of recycling. I find recycling to be far more difficult than people realize. If you use the real word recycling, the ability to take a material and repurpose it in any fashion is near commercially impossible. I know this is a really not the nicest thing to say. If you went on and talked about like remediation, there's lots of incredible work being done. Remediation, I mentioned a little bit right now using mixines. But it is commercially very difficult to recycle anything that has not been originally constructed to be recycled. So the European Union, it's now been 10 years ago, but it hasn't really moved all the way along, established a program that requires that automotive particularly eventually only be developed where every part can be shown where it goes once that car is no longer in use. And without, I would say that would be my biggest comment, which is really not a technological comment, is that unless you have planned the obsolescence and recycling of a given part, and it's been developed, and you have processing plants to work with that bumper or that brake or that piston to recycle it and know where the market is for that, you're never going to get there. The concept that you see, you know, on news like CNN, where somebody's picking through cell phones and pulling out this, that, and the other, it's not commercially viable. You know, there's people that are pulling the platinum out of carburetors. You know that you've got a little bit of platinum in them in the smog systems. That's platinum. You know, obviously platinum works. But recycling of materials is extremely difficult. And you actually raised a very interesting point, which I hadn't really thought about. I'm going to ask some people back at the company. With all this new development in ceramics for materials, you're actually going in the wrong direction, because these are not recyclable materials. They're cheap, useless materials that really have no carry-on purpose. And we're moving as a world in a direction of using materials that have even lower value for recycling purposes. So it's a fascinating question now when you think about it, because I don't think we're moving in that direction. I think we're going to produce a lot of junk when you consider it from a recycling point. Very, very interesting question.
Okay. Thank you.
All right. Thank you. Yes.
Thank
Thank
you
you.
for a nice presentation.
Thank you.
I was wondering about biomaterials, bioconjugated, for instance, polymers, especially in biomedical application, pharmaceutics. Do you see any place for these materials in future 5 years?
Well, absolutely. You know, I mentioned the one, which is just one application. I didn't explain what remdesivir is, but it is a inorganic material. So here you're really actually working with an inorganic for that purpose. We also developed another material recently with, I can't remember who the pharmaceutical company was involved with, for removal of potassium from the blood. A lot of the cancer treatments and various treatments now are potassium is the cation on the material. So you have this potassium buildup in the body, and we developed a material that can go in, and potassium, you can imagine, it's so soluble, you can't really do anything with it. But this actually traps it in a molecular box and removes it. And again, that's another inorganic material. I think of advanced materials as primarily inorganic versus life science materials, which are primarily organic. So you're starting to see more and more inorganic materials in biomedical applications. The last example I would give would be the one that I mentioned earlier, which is this incredible use of a metallic cation on an organic ligand. So now you've integrated advanced and inorganic materials into an organic application. And the day that comes when a person comes into the hospital and sorry, but your tumor's metastasized, that's basically tell your family this is it. we may someday be able to put this material in, radiate the body, and remove all cancer, which would be an incredible application. So yeah, lots and lots of advanced materials now going into pharmaceutical applications. Well,
Thank you very much.
yeah, thank you all very much. This was really fun.